All right, let's dive into one of the most incredible engineering feats of our time. We're talking about the microscopic magic that powers, well, literally everything in our digital world.
I mean, have you ever really stopped and thought about how impossibly powerful that phone in your pocket really is? The journey from the very first computers to what we carry around today, it's not just an improvement. No, it's a total transformation that honestly kind of defies belief. Just look at the scale of this. It's wild. The original 1976 Apple computer, it had a processor chugging along at 1 megahertz with a few thousand transistors. A MacBook Pro today, it runs over 4,000 times faster and packs billions of them. That's not just getting a bigger car. That's like going from a horse and buggy straight to a starship with warp drive.
So that brings us to the big question, right? How is this even possible? How do we build something so powerful, so unbelievably complex, that it's smaller than your fingernail? Well, the answer is a technology with a pretty simple name, but a totally revolutionary impact.
That technology is VLSI, which stands for Very Large Scale Integration. So what does that mean? In simple terms, it's the master plan for cramming an unbelievable number of tiny electronic switches, we call them transistors, onto a single chip. It's the reason we can have these microscopic brains running all our devices.
Now, this didn't just happen by accident. This whole miniaturization revolution was driven by an idea so powerful, it became the guiding star for an entire industry, pushing engineers to do what seemed impossible, year after year after year. And the progress was just relentless. You know, back in the 50s, a chip held maybe 100 transistors. By the 70s, we hit thousands. Then VLSI came along in the 80s and pushed it to millions. And today, we're at what's called gigascale integration, which means we're packing over 1 billion transistors onto a single chip. The pace is just absolutely staggering.
This insane pace was famously observed way back in 1965 by Intel co-founder Gordon Moore. His prediction, which we now call Moore's Law, wasn't some law of physics. It was more of an observation that became a self-fulfilling prophecy. The entire tech industry basically organized itself around this goal. Okay, we're going to double the density every 2 years. Let's go!
So how do they actually make one of these chips? Honestly, the best way to think about it is like designing and building a massive, incredibly intricate, multi-layered city, but all on a microscopic scale. And it's a process with a very, very clear blueprint.
The whole thing is broken down into 2 main phases. First, you've got the front end. You can think of this as the architect's office. This is where the idea is born, where the chip's function is defined, and all the high-level plans are drawn up. Then you have the back end. This is the construction site. This is where those abstract plans get turned into a real, physical, working piece of silicon.
So once we get to the construction site, that back-end phase, it all starts with something called floor planning. This is basically like zoning our Silicon City. You're deciding where the big neighborhoods, like the CPU and the memory, are going to go to make sure everything is super efficient. It's all about preventing data traffic jams before they can even start.
Next up is routing. And this is where things get mind-bogglingly complex. This is the process of laying down all the microscopic roads and superhighways. We're talking sometimes more than a dozen layers of metal wiring that physically connect every single component. Just try to imagine wiring an entire city, from the interstate highways down to the last outlet in one apartment, all in a space smaller than a postage stamp. It's incredible.
And all of this work, all that planning and wiring, it all comes together in the final layout. This is the master blueprint of the entire chip. It shows the exact physical location of every single last transistor and wire. This is the incredibly detailed map that gets sent to the factory, the fab, to actually be built layer by painstaking layer.
Okay, but here's the thing. Just like you can build a house in different ways, chip designers have different strategies. Not every chip is built from the ground up from scratch. They pick their approach based on what the chip needs to do, how many they're going to make, and of course how much it's all going to cost.
So designers face this huge choice, and it's all about trade-offs. On one side, you've got something called an FPGA. These are amazing because they're super flexible. You can reprogram them. They have a low upfront cost, and they're great for testing out ideas. On the other side, you have ASICs. These are totally custom built for one specific job. They cost a fortune to design, but they give you the absolute maximum performance, and they get cheap when you make millions of them.
You know, here's a really simple way to think about it. FPGAs are like a giant box of programmable Legos. You can build anything you want, and if you don't like it, you can just take it apart and build something totally new. ASICs, on the other hand, are like a Formula One race car engine. It does one thing, and one thing only. But it does it faster and more efficiently than pretty much anything else on the planet.
What's really cool is that in the real world, in products like Apple's bionic chips, they don't just pick one. They use a brilliant mix. It's what we call a system on a chip. The GPU for graphics and the neural engine for AI, those are ASICs. They're the custom race car parts. But other components use more standard, pre-designed blocks to save time and money. It really is the best of both worlds.
All right, so we've been deep in the weeds of this microscopic world of chip design. We've talked about floor planning and Legos and race cars, but why does any of this really matter? Why should you care about how these tiny silicon cities are planned?
Well, the answer is actually pretty simple. VLSI isn't just a technology. It is the foundational layer that our entire modern world is built on. Without it, almost nothing that we take for granted today would even exist. It's what makes the microprocessor in your laptop and the memory chips in your phone possible. It powers your smartphone, your laptop, your smartwatch. It drives the entire Internet of Things. And, crucially, it is the reason our gadgets keep getting smaller, faster, and more power efficient with every single generation. It is the engine of all technological progress.
So here we are. We have literally learned how to build microscopic cities with billions of inhabitants that can think at the speed of light. But as we start pushing up against the absolute limits of physics, and Moore's law begins to slow down, the biggest question is still out there. What comes next? What new architectural blueprints are we going to invent to design the future of technology?